Welcome to Power Electronics Education Electronic Book, Lecture 4, Control Rectifiers. This lecture is presented by Dr. FIRUZ ZARE. The contents of this lecture are control circuit, single phase half wave control rectifier, single phase full wave control rectifier, three phase half wave control rectifier, three phase full wave control rectifier, single phase full wave half control rectifier, and three phase full wave half control rectifier. So this is a block diagram of a control rectifier which basically convert the AC voltage into DC voltage. So what's happened here, we have a controller because this is control rectifier. So using this controller we can generate pulse voltage. That means we can determine 10 on time because this is based on thyristor or SCR. That means we can just apply gate signal to turn on the thyristor. So we cannot turn off the thyristor by removing the gate signal because this is a special switch. So in this case, by changing the gate signal, we can basically control the output voltage. Because if we have an AC voltage, we can determine when turn on the thyristor or when switch the thyristor to provide this voltage across the load. So that's why by changing this firing angle or by changing this time, we are able to control this area which defines the output voltage. And in some applications we have, for example, full wave control rectifier. That means we can also rectify the second half a cycle. So this depends on the topology and the output voltage depends on this firing angle. So control rectifier, either a single phase or three phase, are based on thyristor, which should be turned on using a control signal. So if you look at the cycle and line frequency, so we can find different times or different switching times. For example, if the line frequency is 50 Hz, that means one cycle based on 50 Hz is 20 milliseconds. So one way to define the switching time is based on this cycle. That means starting from zero crossing, this time will be 20 milliseconds, and first half a cycle, this time is 10 milliseconds, or a quarter of that one is 5 milliseconds. So because in different applications we may have 50 Hz or 60 Hz, so that's why we may have different switching times. Another definition is based on firing angle. That means one cycle is 2 pi. So this angle is 2 pi while this time is 20 milliseconds in a 50 Hz system. So this angle is pi. So this angle is pi over 2. So sometimes we can define the switching time or sometimes we can define the firing angle, which basically they are same but different definition. So in this case we can also define based on degree. So instead of 2 pi we can say 360. So instead of pi we can say 180, or instead of pi over 2 we can say 90. This circuit diagram describes a control system for control rectifier. We need to generate a sawtooth which has to be synchronized with input voltage. So in this case, we need to sample the input voltage and send the signal to this sawtooth generator. And then using either analog or digital system, we may generate this sawtooth. So how to get this gate signal? By comparing reference voltage, which is basically here, this green line, with this sawtooth, we can generate our pulse voltage, which defines the turn on time. So basically this time, according to input voltage, this cycle is T/2. And suppose this time is T1 or T on. So if this is V reference, so suppose the peak of sawtooth is V sawtooth. Now we can find this time in terms of these parameters. If you look at this small triangle, the ratio of this side over this side is T1 over T/2. Which is equal to the ratio of this side, which is V reference, over this side, which is V sawtooth. So V reference over V sawtooth. So T1 is T/2 times of V reference over V sawtooth. So basically line frequency is constant. That means line frequency is constant, or this cycle is constant. So this term is constant. Suppose that we generate sawtooth with constant peak voltage. So that means this term is constant. So T1 equals to T/2 times of VST sawtooth times of V reference. So this term is constant. So by changing the reference voltage, we can change the switching time. We can also define this one in terms of radian or degree. So then we can define also alpha, which can be pi over VST times of V reference. The reason is that T/2 equals to pi. So we can find the firing angle in terms of reference voltage and other parameters. This is a single phase half wave rectifier with resistive load. Input voltage is a sine wave. So we apply gate signal at this firing angle. That means a gate signal is applied to this gate terminal just at this instant of time. So because starting from this zero crossing point, current through the thyristor is 0, thyristor is off, and now the output voltage is 0 until this time. And now we can see that just at this firing angle we apply gate signal because the voltage across the thyristor is positive, and the reason is that over first half a cycle input voltage is positive. So by applying gate signal we can turn on this thyristor. So from this time we have output voltage which is equal to input voltage because input voltage appears across the load. So at this zero crossing, because current through the thyristor is 0 and beyond this time it will be negative, so that's why thyristor will be turned off again. So for the second half a cycle the output voltage is 0, and the reason is that thyristor cannot conduct. So basically this is output voltage. That means by changing this firing angle we may have different output voltage. So if I change it to this firing time, then I can increase the output voltage. So that means by changing this firing angle I can control the output voltage. If you look at the voltage across the thyristor, the time that this thyristor is off, that means the voltage across the resistor is 0. So that's why this is basically input voltage appears across thyristor. Over this period the thyristor is turned on, so suppose the voltage across the thyristor is 0, and again because thyristor is off, again input voltage appears across the thyristor. So this is the voltage across the thyristor. If we look at the output current basically depends on load impedance, because current is voltage divided by load resistor, and you can see that the current waveform is similar to voltage waveform because we have resistive load. So as we convert the AC voltage into DC in control rectifier, so it's quite important to find the output voltage in terms of firing angle and input voltage. So this is input voltage. Suppose we apply this gate signal just at this time, which is defined T1. We can also define based on firing angle of alpha. So then we can define the output voltage, which means that output voltage is 0 up to T1, and then we have output voltage here, and then we have no output voltage till end of this cycle. So the point is to find this area which defines the average output voltage. So based on this simple equation we can find the output voltage over one cycle. So now we need to find and put in this equation, because we have output voltage at different periods. So if you look at the limits of integral in this equation, because the output voltage is 0 up to this time, so that's why the first term is not considered, and we just define the limits of integral from T1 up to T over 2, which is basically this time and this time. So this sign, the integral of this sign is minus cosine 2 pi t over t. We have the limits of integral, and then we can simplify this equation. That means we can cancel t, Vm over 2 pi. This is the constant term, and then if we put the upper limit, that means minus cosinus 2 pi t times of upper limit, which is t over 2, and then this one is minus cosinus pi, which is basically this term, and when we put the lower limit we get this term. So finally we can simplify this equation, because cosine pi is minus 1, minus times of minus is plus, and the second term is cosine 2 pi t1 over t. And then we can define this one in terms of alpha, because if this one is t1, we can define t1 in terms of alpha, because one cycle is t, in radian is 2 pi. So if t1 in time frame equals to alpha in this radian, so from here we can find t1, which is alpha t over 2 pi. So if you put this one in this equation, so cosine 2 pi over t times of t1, which is alpha t over 2 pi. So this one equals to cosine alpha. So here we can define another equation which is almost same based on different variable. So here we can see that by changing alpha or by changing t1, we can define and we can change the output voltage. Now let's analyze a single phase half wave rectifier with RL load. So here we have resistive and inductive load. Suppose that we apply gate signal at this firing angle. So we apply gate signal to this thyristor just at this time or this firing angle. So starting from zero crossing, that means the current through the circuit is 0, this thyristor is off. So over this time, thyristor is off. And now we just apply gate signal at this time. Because the input voltage is positive for the first half a cycle, that means we have positive voltage across the thyristor. So if we apply gate signal, we can turn it on. So what's happened when we turn on the thyristor? Input voltage appears across the resistive and inductive load. So then we can increase the current. So the current through the thyristor, that means load current is increased. And the point is that at this zero crossing point, if you look at the load current, so load current or output current is not 0. So that's why the current through the thyristor is not 0. So that's why thyristor conduct. But just at this point, at this time, because the current through the thyristor is 0 or output current is 0, so that's why thyristor is turned off. So here thyristor is off. So we can see that the output voltage corresponds to this area plus that area. So then we can see that the output voltage depends on load impedance, and we need to find this time, turn off time, to be able to find the output voltage, because we know this time and we have to find turn off time. So this is a battery charger based on a single phase half wave rectifier, which basically consists of inductive load in series with the battery. This is the inductive load and this is battery. So when we apply gate signal, we may turn on the thyristor and then charge the battery, but the key point is that we have to be sure that the voltage across the thyristor is positive when we apply gate signal, because when the input voltage is lower than battery, then the voltage across the thyristor is negative. So that's why we cannot apply gate signal. But once the input voltage becomes greater than battery, then the voltage across the thyristor will be positive. In this case, we can apply gate signal to turn on the thyristor. So this firing angle should be calculated based on this voltage and input voltage. So what's happened? When we apply gate signal, we turn on thyristor. That means over this time, the thyristor is off. And because the current through the battery is 0, So the output voltage, which is basically equals to battery's voltage, and over this period thyristor is on, thyristor is on, and if we look at the zero crossing or any point except this time, we can see that the current through the thyristor or output current is positive. So that's why thyristor is on and is on over this cycle. And just at this point, because the current through the thyristor becomes 0, so that's why the thyristor is getting off. So over this time or this period, thyristor is off, and that will be the output voltage. So in this case, we can find the maximum current, the average current through the system, and basically by changing the inductor's value, we can control this current. That means we can control the average current through the battery, or we can define and control the charging current for this system. This is a single phase full wave bridge rectifier based on resistive load, similar to a diode rectifier. When we have a positive voltage, this thyristor and this thyristor have positive voltage, but they are in off state because there is not any gate signal. So once we apply gate signal just at this time or that firing angle, then we can turn on thyristor 1 and thyristor 4. That means we have to apply gate signal to both thyristors to be able to turn on these thyristors. So what happens when we apply gate signal? Then input voltage appears across the load. So that means over this cycle we have input voltage across the load, and this is the current loop. That means the current pass through thyristor back to the load, back to thyristor number 4, and then back to the supply. At this zero crossing, because the current through the load or output current is 0 and is getting negative, so that's why these thyristors are getting off. If these thyristors are off because these two were in off state, so the output voltage is 0. So in this case, T1 and T2 are on, but T2 and T3 are off. Here all are off, and here again, because we turn off T1 and T4, all thyristors are off. Now in the second half cycle, with respect to this zero crossing again, we apply gate signal to these thyristors. So what happens here? Again, we can turn on this thyristor. The reason is that when the input voltage is getting negative for the second half cycle, similar to diode rectifier, we have positive voltage across these thyristors, but these are not on because still we haven't applied any gate signal. So once we apply gate signal to this firing angle, based on this firing angle or this time, then we can turn on these two thyristors. Again, because the input voltage appears across the load with positive polarity, because once this thyristor is on, the positive point is connected here and the negative point is connected here. That means still we have positive voltage, and this is the current loop from thyristor 3 back to the load, thyristor 2, back to the supply, and through this line back to the thyristor 3. So this is the output voltage for the first half a cycle. This is the output voltage for the second half a cycle. So in this case, T2 and T3 are on, but T1 and T4 are off. What about input current? So basically input current, because we have resistive load, so output current is basically output voltage over resistor. That means output current, the waveform is similar to voltage waveform. For the first half a cycle, the input current same as output current, but for the second half a cycle, because of turning on these thyristors, the direction of current is changed. So we have almost same current waveform in different polarity, in different direction. So you can see that the input current is not sine wave. That means this current has harmonics. So in high power converter, we have to control the harmonics, and we have to reduce either by passive or active filters. So we can find the output voltage of a single phase full wave rectifier based on this equation. For example, the output voltage is basically based on this integral. Again, we can find this integral, which is basically comes from this voltage waveform, because this voltage waveform means that we have to calculate this area plus this area, which defines the output voltage. In the previous rectifier, we already calculate this part, and because this area is almost same as this area, because the firing angle is same, so that's why in this case we can just concentrate on one of these area, which starts from T1 till T over 2. So that's why we can simplify this equation into this equation. And then from the previous equation, we have found this integral, which was basically Vm over 2 pi 1 plus cosine 2 pi T1 over T. Or we can simplify this equation with Vm over pi 1 plus cosine 2 pi T1 over T. Similar to the previous case, we can say that alpha equals to 2 pi T1 over T. So the output voltage in this case, when we have full wave rectifier, is Vm over pi 1 plus cosine alpha. So if alpha is 0, that means Vm over pi times of 1 plus cosine 0. So this cosine 0 is 1. That means 2 Vm over pi, which is basically output voltage based on diode rectifier, because when alpha is 0, that means this is the output voltage, which is full wave diode rectifier. So here you can see that by changing alpha, we can control the output voltage.